So we're looking at the complications. Really, is what all of Unit 3 is associated with, and we have looked at the more common complications of prenatal time period and the immediate postpartum time period in Unit 3A. Okay? 3B focuses on genetic issues because it can kind of cross-span between mom and baby. And then Unit 3C, I tend to get a little passionate about, and that's just because babies are my deal. And that one talks more about the complications that can occur for our neonates. So as I mentioned, genetics kind of plays a part between both mom and baby because perhaps mom has a genetic disorder that complicates the pregnancy, or perhaps the fetus develops a genetic disorder that complicates the pregnancy. So we're going to look at single gene disorders. We're going to look at autosomal dominant, autosomal recessive, X-linked recessive, X-linked dominant. You're going to be having a brief introduction to Punnett squares, and we're going to look at common disorders associated with inborn errors of metabolism. So first of all, let's just talk about something here really quick. We're going to be doing like this little anatomy review, or I'm going to recommend that you do a little anatomy review on your own. But first, let's talk about terminology. So terminology, remember, what are chromosomes? Let's get real basic here, people. So chromosomes are those really tiny thread-like strands of DNA. We have 46 total chromosomes. Okay, so we have 22 autosome control traits. These are controlling kind of the identity of an individual, and then a sex chromosome. Okay, so then we have doubles of all of that together, and that gets to our 46 chromosomes. Alleles. This is a variation of a trait. There are two genes each inherited, one from the mother, one from the father. But even though we pair them up, so even looking over here, on your left-hand side, we've paired all of these genes up exactly where they need to be. But, this number 11, the red marking isn't exactly the same. Oh, heavens to Betsy. It's not exactly the same between the one on the left and the one on the right. Well, why? Because there are alleles. Homozygous genotype. Basically here, both inherited genes are the same, but the alleles can be different. Okay? And then you can have a heterozygous genotype wherein both inherited genes are different. So look down at number 18. See, for anybody who's colorblind, I really apologize. But the one on the left, that gene is a little bit more purple, whereas the one on the right is a little bit more pink. So again, they match up together. The genes sequencing, like the identifying marks that say this is gene number 18, whatever, are there, so they pair up, but the alleles are different. Okay? Well, the alleles here, this is where we start talking about dominant and recessive. So the effect of one allele in a heterozygously different gene is going to completely mask the effect of the other. So then, that's where we start talking about dominant. That particular allele, that little key in that puzzle piece, that one is dominant. Okay, so in this number 18, only one can be king, all right? There can only be one expression So when we talk about hair color, for example, you might see like a little bit of differences between hair colors per se, but for the most part we have what? Brown hair, black hair, white hair, red hair. Our hair is either curly, our hair is straight, you know, those kind of things. Those all refer to the hair gene or a hair color gene. But if you have a parent with brown hair and you have a parent with blonde hair, or a parent with straight hair and a parent with curly hair, chances are you're only going to have one of those. You can't have both straight and curly hair. Well, most days, right? So there's going to be a dominant allele, and then there's a recessive. So it's there. Like, it is, you are still carrying it, but you just can't see it. It's shy, it's recessive, it recedes behind the main scene. What's the reality here? The reality is that most of us carry some form of a genetic disorder. And genetic disorders are entirely and completely common. Most chromosomal or abnormalities that occur in the first trimester relate to spontaneous abortions. Other genetic disorders we don't necessarily see in utero, but they become apparent later in life. So that's really where, when we talk about this cross-matching between pregnancy and postpartum and the neonatal time period. When all of us are carrying some form of a genetic disorder, what we're going back to is whether it's dominant expressed or recessive, as to whether or not perhaps that genetic anomaly is expressed. So again, a chromosomal abnormality or disease can be transmitted by, or is transmitted by, heredity. So these are inherited. Again, like I mentioned, it's either going to be dominant or recessive. Either it's going to be apparent or it's not going to be apparent. Apparent as in clear, not as in mom or dad. Okay. Single gene disorder etiology. When we're looking at autosomal dominant inheritance, what we're talking about here is a dominant gene on an autosome. Autosome, not a sex-linked chromosome. So we have an abnormal gene, and that abnormal gene is dominant. It doesn't care that its friend right next door is normal. It pushes them out of the way and says, I am here, I am needy, and I will be expressed. Okay? Autosomal recessive is, hi, I'm a genetic disorder, but again, I'm shy, and so I'm going to stay over here in the back and let my friend take over, who's completely normal. Okay? X-linked dominant, this again is that same kind of concept as the autosome, except it's on a sex chromosome. And it can be mom or dad, and we'll get into that here in just a second. X-linked recessive, same thing as the autosomal recessive, except it's on that sex chromosome. So then we have this introduction to Punnett squares, and we'll play this video.
Hi, my name is Mary Poffenroth. I'm an adjunct professor of biology, and today we're going to have a little fun with Mendelian Punnett squares. Now, before we get started and jumping into our Punnett square problems, let's set down some ground rules. First, we're going to talk about alleles. Alleles are going to be like different flavors of genes. So, you go into the ice cream shop, there's 31 flavors of ice cream. Even though they're all different flavors, they're all still ice cream, right? Alleles are going to be those different flavors of genes that you have available to you. The next thing I want to talk about is dominant and recessive. In any relationship, some of those alleles are going to be dominant, and some of those alleles are going to be recessive. Those dominant alleles, if they're present, they're going to have more of a say in what the outcome of that cross is going to be. And the recessives, well, they're going to have little to no say unless there are two recessives that are available. Also, in each of our crosses, we're going to have one allele from our mother and one allele from our father. Now, let's jump into our crosses. Today, we're going to do a 4-square Punnett square. So, you want to start out by just drawing a square. In that square, you're going to draw a line right down the middle from the top to the bottom and a line from left to right. Now, you have 4 individual squares. Each of those squares is going to be a probability, and each of those squares is 1/4, right? Or 25%. Next, we're going to put our parents' alleles on the Punnett square. Now, it doesn't really matter if you put male or female on the top, but generally people put male on top, female to the left. For our problem today, we're going to use eye color. The eye color alleles are going to be, for our father, it's going to be brown phenotypically expressed alleles. That means that father has brown eyes, but his genotype, or the genes at play, his alleles are going to be big B, little b. That means that he's heterozygous, or he has 2 different alleles for that trait of eye color. It's a little important to note at this time that all of these letters are completely arbitrary. You can make up any letters you want. However, in any relationship, a capital letter or a big letter, like say big B, is going to be for the dominant. And a little letter, or a lowercase letter, in this case little b, is going to be for the recessive. Okay, so we have the father, big B, little b. He's heterozygous, meaning he has 2 different alleles. What about the mom? The mom has blue eyes, so phenotypically, her expression that you see on the outside is blue eyes. Her genotype, or the genes at play, are going to be little b, or homozygous recessive. Alrighty, it's time to do our cross. Now, we're going to take one from the top and one from the left, and we're going to bring them down into those squares. So, we have on our top, big B, little b, then bring another big B, little b down. In our right square at the top, we have little b, and our bottom right square, we have little b. Okay, what does that mean for the probability of getting an offspring with what kind of eye color? Now remember, each of those squares is going to be 25%. So, we have a 25 plus 25 or 50% chance of getting an offspring with brown eyes. And we have a 25 plus 25 or 50% chance of getting an offspring with blue eyes. And for a fun little extra problem when you're sitting around the dinner table, take the eye colors or the phenotypes of your parents. Even though you won't know the exact genotypes or the genetic makeup behind what you're seeing on the outside, do some crosses and see if you could find out the probability that you could have actually had a different eye color. Thanks for watching.
Okay, so hopefully that just elaborated a little bit more on some of the terminology, but also drawing a Punnett square, which is one of your learning objectives. So now let's look about how this impacts what we're concerned about with genetic disorders prenatal and in the neonatal time period. So again, autosomal dominant inheritance. So in this case, all right, the abnormal is saying the one that needs all the attention and pushing the normal off to the side. So the corresponding gene, so a person's going to carry both, right? The corresponding gene is recessive. So either in this case you have a 50-50 chance of having the disorder and a 50% chance. In this case, there will be no carriers. There will be a little bit of this expression in every generation, but it will be at varying degrees. Males and females here, because it's not a sex-linked chromosome, males and females are going to be affected equally. Alright? So you may not have this, may not express this, but maybe your cousins will. That's what it means in every generation. Okay? These include Huntington's chorea, neurofibromatosis, which causes tumors to form on nerve tissue. Doesn't that sound lovely? Ooh, sounds so painful. And achondroplasia, which is the most common type of short-limbed dwarfism. Then let's talk about autosomal recessive. So in order for this to be expressed, both of the genes have to be abnormal. So in this case, we have, and you'll see this as well, it's a homozygous trait then, right? If both of them have to be recessive, then that individual doesn't have a choice. They're not going to be a carrier. It's going to be a straight homozygous trait. Now, with that being said, 25% are not affected at all. 50% are carriers, and 25% are the affected child. Many of these children have had no family history of the disorder. Well, why? Because their parents were both affected carriers, or unaffected carriers, excuse me. So they perhaps didn't realize that they were carrying this genetic disorder on this autosomal recessive gene, and it's not until after delivery or during a prenatal workup, during the not preconceptual but prenatal workup, that we find out that the root cause of it was unknown autosomal carriers. Again, we all have abnormal recessive genes. We all carry some form of genetic disorder, but they're not expressed because the other ones, the other genes, are being expressed as dominant. Many of these autosomal recessive disorders are the inborn errors of metabolism, which are referenced in your discussion post about newborn metabolic screenings within this chapter, or within this unit, excuse me. But most often what we have when we're talking about a metabolic disorder is a lack of or a deficiency in some particular enzyme, and it's impairing the body from being able to appropriately and properly metabolize food components, things like proteins, fats, or carbohydrates for basic metabolic function. Enzymes are definitely needed for those physical and chemical processes to occur. And so when we have a deficiency in one of those areas, we can have either an excessive accumulation or a severe deficiency within the metabolic process. Both of those are very, very concerning. Some of these inborn errors of metabolism can be managed just by simple dietary changes. For example, PKU, which is an increased level of phenylethylamine in the blood. Phenylethylamine is a building block of proteins, so it's an amino acid. It's obtained from the diet. However, that excessive accumulation of PKU will start to inhibit metabolic processes and will inhibit normal homeostasis and function. PKU, or phenylethylamine, is also found in a lot of artificial sweeteners, and in addition to being in all proteins. So PKU positive individuals, they have to have a diet. They would not do well on the ketogenic diet, right? Because the ketogenic diet is all about protein. So these individuals have to have a very limited diet of protein intake, and they need to avoid all of those artificial sweeteners. On the back of your gum and on the back of your Diet Coke, you'll see where it says contains phenylethylamine, and that's extremely important for these individuals who have a PKU positive indicator. Maple syrup urine disease is very similar to that, and that's another one of the disorders that's frequently picked when you guys do your newborn metabolic screening, just because of the name. I think people get really intrigued by that. But again, we're going to manage that particular disorder by, again, limiting the protein intake. Other disorders that are autosomal recessive have absolutely nothing to do with diet or enzyme or protein absorption, but have to be managed in other ways. And this refers to cystic fibrosis, our sickle cell kids and adults. Again, you're going to see this as a carrier in 50% of individuals who carry this gene. X-linked dominant inheritance is going to be caused by an altered gene present on the X chromosome. So it's a sex-linked disorder. It can be inherited either dominant or recessive. Remember, however, when we're talking about sex-linked disorders, that how many X chromosomes do males have? They only have one, whereas women have two. So if the altered or abnormal gene is on the X, the male will express this disorder. So X-linked dominant inheritance is actually very rare. Because this gene is very dominant, it only needs to be on one X in order for the disease to occur. The affected father will have affected daughters because he's passing on that X chromosome. There is no male-to-male transmission. Why? Because the father is passing on only his Y to his son. Some of these examples include hypophosphatemia, which is a form of rickets that's congenital, and another disorder that's called incongenta pigmenti, which in males is actually lethal prior to birth, but in females it will cause highly variable abnormalities of the skin, the hair, the teeth, the nails, the eyes, but also most importantly the central nervous system. X-linked recessive accounts for the majority of your X-linked disorders. Now, these ones are a little bit different for the mother or for the father. So if the mother, for example, is carrying the X-linked recessive inheritance, if she is carrying the recessive abnormal gene, she didn't know that she had it, her normal X overshadows her recessive gene. So this includes things like color blindness, Duchenne's muscular dystrophy, typically, which Duchenne's only affects males. Typically, there are other types of muscular dystrophy that are not X-linked recessive, or they're just like a spontaneous mutation. Hemophilia A typically also only affects males. Again, like I said, I'm a little bit of a historical royal Queen of England buff. It drives my husband nuts. But Queen Victoria is thought to have passed on hemophilia A, I believe, to all of her children, which led to a lot of the boys passing away at very early ages of life. If the father is the carrier, there once again will be no male-to-male transmission, and all of the daughters, as he passes along his X, here you go, here's your X chromosome because you're going to be a girl, right, will be carrying that recessive disorder. So those are genetic disorders that are hereditary. But as I already mentioned when I was talking about muscular dystrophy, there are times when just spontaneous mutations occur. So some of these include non-disjunction, which during cell division, what that is talking about is uneven chromosomal development, cell division, numerical changes, just something didn't fit right. So these include like your trisomy disorders, where you might have 3 chromosomes instead of 2. And that's usually indicated in decreased MSAFP results during prenatal testing. Some of your common trisomies, trisomy 21, commonly known as Down syndrome, trisomy 13, Patau's, trisomy 18, which is Edwards syndrome. Our kids with Edwards and Patau's don't always get to live a long life. The chromosomal disorders have done so much damage to their overall health that it's not always sustainable with life. There are success stories out there. I have seen children who do remarkably well against all odds. You think that they're set up for failure, and they do beautifully, and they grow and they flourish in their little families. And there are other children who unfortunately are not able to do that. Structural abnormalities refers to chromosomes that are partially broken, or somehow a deletion occurs during the whole process of cell division. Translocation means incorrect gene sequencing. So instead of matching up like straight across from each other, these guys are kind of off a little bit, and then the wrong genes line up. Sex-linked genetic abnormalities. These ones are kind of near and dear to my heart. I have a family member with one of these disorders. Actually, I have two. Turner syndrome is found only in females, and Klinefelter syndrome is found only in boys. These sex-linked disorders are when we have multiple anomalies with the gene sequencing with the X or the Y, or the sex, meaning the X chromosomes. So in Klinefelter syndrome, it's also called XXY. So these boys carry this extra X. The extra X correlates to hypogonadism, and the hypogonadism correlates most frequently to infertility. Klinefelter syndrome is not typically diagnosed, or historically has not been diagnosed, until a man chooses to reproduce and finds that he is unable to do so. Individuals who are affected by Klinefelter's and Turner syndrome are unable to have children of their own. And unfortunately, Klinefelter syndrome and Turner syndrome run the gamut. You can have somebody who has just that inability to reproduce, and you have other children along that whole with that same diagnosis who struggle in school and are diagnosed with other disorders that are at increased levels along with these Turner and Klinefelter syndromes. There's also multifactorial, which is a combination of genetics and environment. So basically, you might have had like a genetic predisposition, but it might not have been expressed unless like a nuclear bomb went off or something just really wonky happened. And this includes like cleft lip or a cleft palate. I was actually born with a cleft palate. But not the lip. And my parents did a complete genetic workup after I was born, because they were trying to pinpoint why I had this cleft palate and something else called Pierre-Robin. And they were unable to identify it. There was no known genetic cause. So at this point, we just say it's environmental. So it's a congenital anomaly that occurred. And the experts believe that I had my tongue on the roof of my mouth during that time when that should have been forming. And so at the age of 10 months, I underwent surgery at what was Children's Memorial and is now called Lurie's Children's Hospital along the lake in Chicago. Neural tube defects, congenital heart defects, and club feet. They all follow along in this multifactorial situation. So there's nothing any of us could have done to prevent these things from occurring. And that concludes our discussion about genetic abnormalities.